if my Wi-Fi goes down. Internet is back. It was going out earlier. Internet is back. It's going out earlier. One second, bring up my back channel with my chair. Let me pull up the agenda too. Getting the agenda. I just like to have this separately so that I can get to it without having to have the chair slide. Okay, let's get started. Audio's good? Sweet. All right, thank you all for attending this session of the Congestion Control Working Group, especially in our heavily conflicted slot with some other major working groups. A brief reminder that this session is being recorded and we're using the queue, so if you'd like to speak at the mic, you know the drill. Make sure that you've scanned the QR code over there. That also helps us make sure that we have a record of who was here so that they continue to give us nice large rooms to have these fun meetings in. A quick reminder to actually please read the note well. Don't just look at it and nod your head and smile. This is the terms under which we participate in the IETF, which especially covers certain IPR and patent disclosure requirements that you agree to by participating here. Also note that we abide by a code of conduct, so please treat everybody with respect. And if you experience issues, you can come talk to us as the chairs or the OSBUD team. We've got a couple of helpful links if you're looking at a PDF version of the slides. And with that, we have a super packed agenda today. So we're going to try to jump right into it. That said, you'll notice there's a rechartering discussion a little bit later on in here. So in our previous session at 119, we had a bunch of really good signals from the group about, hey, these are the kinds of things that we'd like to work on as we've wrapped up 5033 bis. And so this time, we're going to go through a number of these different proposals and actually talk about, hey, these are specific drafts. How many of them do we think we can work on at the same time? What would we like to adopt first? What do we want to move forwards with? So the context for each of these presentations is be thinking about, is this something that the working group wants to spend time on? Are people ready to review and deploy and implement and actually read these documents? And especially of interest for us as chairs, how much do we think we can take on at once in a group? It seems unlikely that we're going to do like 6 different congestion controllers all simultaneously at the same time, especially because that would deprive us of the opportunity to learn from one and apply those learnings to the next. So with that in mind, first up, oh, good call, yes. Would anybody, while Michael's getting set up to talk about rate limited sending, would anybody like to volunteer to take notes? And as I mentioned in another session this week, you're distinct. Thank you, Gory. You are wonderful. While everyone else was distinctly interested in their laptop, that is an awesome moment to make sure that you're on the MeetEcho page in your browser so that you can participate in some of the show of hands and polls and things that we'll be doing. Thank you so much, Gory. All right. With that, we have a solid 15 minutes. Let's take it away.
Okay, thank you. This will be a short one. It's meant to be a bug fix of a strange oddity in the specifications that we have. About when the sender is application limited. It all began with me looking at NS3, where they were implementing the spec true to the spec, and seeing a plot like this, which is just completely wrong and odd and strange in every possible way. And I said, oh, NS3 must have a mistake in there, but it turns out it's a bug in the spec. Our spec absolutely allows that when the application is limited or the receiver limits the sender, but you keep on sending, just not the full congestion window. You can grow forever, and then you have that window that is ready to use. So the primary motivation of this is just to fix this with a proposed standard RFC. That's what this is about. Another reminder, this is all unchanged since the last presentation. We proposed two rules. One is a must that just says you should, well, not allow what you just said, right? Include a limit to the growth of the congestion window when flight size is smaller than the congestion window. And then we make a concrete proposal, but with a should, which says you should limit the growth of the congestion when the flight size is smaller than the congestion window, with a function call, which is a generic increase as a function of the maximum flight size, which, so the increase function will be whatever the congestion control algorithm would now use to increase. For instance, TCP in slow start would do a +1, but not on the basis of the congestion window, but on the basis of this maxFS variable. And maxFS is the maximum flight size so far since the last increase. And then in the definition, we have a rule saying, well, yeah, I mean, if congestion window has gone down, you reset it. And at the very beginning, of course, that's also something you can take. Turns out that slow start, the slow start part of the Linux implementation for TCP already does that with rule 2. That's actually exactly what's implemented there. We presented that at the last IETF. Feedback that we got, we tried to incorporate. It wasn't very much feedback. One incorporation was that we have made new subsections on rate-based controls and pacing. The guiding principle behind the rules that we have made is that when there is no congestion indication, a congestion control sender should always be allowed to increase on the basis of what it has sent in the previous round trip time. Right, so if I have sent a window of 100 packets and I'm in slow start, I should in the next round trip time be allowed to send the 200 packets. If the window could have been 150 already, but I only used 100, then that would be the basis to increase. And that logic holds irrespective of whether the sender is rate limited or not. I mean, you have measured something, on the basis of what you've measured, you should be able to increase. Just to finish that slide, pacing normally operates on sub-RTT timescales, so we think there's nothing we need to do to be true to pacing. It doesn't actually affect it. Yes?
A really quick comment, because I don't want to interrupt you, but looking at that slide, I suspect you'll agree with me. In the absence of evidence is not evidence of absence.
The absence of a congestion indication.
In the absence of an indication, there's no congestion. It's just the cliche, right? Absence of evidence is not evidence of absence.
Okay. But yeah, exactly. I carry on. I think this is wordsmithing, nitpicking.
No, I didn't mean to nitpick. I'm sorry if it sounded like that, and I must be not saying it clearly. Saying, I have sent no packets, so I have no evidence of congestion.
Yeah.
That proves I can send whatever I want because there's no congestion. That there's faulty logic there, which is your point. I'm not disagreeing with you. I'm just backing you up that there's some faulty logic there.
Okay.
Just because if you haven't tried to find congestion, the fact that you found none doesn't mean there isn't any.
Exactly. Yeah, I agree with that. But we were just trying to stay true with the regular congestion control logic, right? So we're not changing anything about it really. Next slide, another feedback we got is that, well, we had kind of an open question in the draft of how many specifications should this update, because there are many congestion controls somewhere in the spec here and there. And as a result of the feedback, we trimmed the list to TCP Reno, Congestion Control, Quick, SCTP, and Cubic. And I think that's my last slide. That's what we've done. And we would like the working group to adopt that.
Any comments, clarification, questions? We have Neil in the queue.
Yeah, hi. So I think Stuart's remark is an interesting one to try to take on board and incorporate into this. So one question I have about the way this spec is structured is that it seems that the max FS is over a potentially very, very long time period, since I guess it's since the last packet loss or ECN mark or the beginning of the connection. And so it seems like it's written so that we're using evidence from potentially minutes, hours, days ago to justify the increase of a sea wind now. And so I'm wondering if we might want to structure it so that you can only use the flight size and the most recent round trip time, something like that. That's how the Linux code that handles this kind of stuff is structured, is it tries to look at just the flight size over the last round trip when deciding whether to increase now. And so I think, like, so for example, in Stuart's point, I think is one way we can incorporate it is to say, if we're not sending over the last 2 hours, then that's absence of evidence of congestion, but it's not evidence of absence of congestion. And so we might want to say that we shouldn't be using a flight size that was from before that very long idle period. We should only be using, a recent flight size, something like that. Would that make sense or something like that?
I think my answer is that I think that new congestion window validation makes sense, which is an experimental specification that we have, which addresses this. And yeah, I think that's my answer to that. So I think this should be left up to congestion window validation. And if you don't do congestion window validation, you could have a window of 100 packets and not do anything, and after 10 minutes send 100 packets. If this is in slow start, we would allow 200 in that one round. So that's just staying true with the congestion control specs, I believe. Either way, this is just a should. It's yeah.
Ian Sweat, I want to add that RC 9002 does not have the identical text that you put up there, but it has something that's attempting to be very much of the same shape of the normative text that you proposed adding in section 7.8 about underutilizing the congestion window.
In our draft?
Oh, and
you had
you had some normative text at the beginning of these slides.
You're saying this is not matching the text from the draft? I'm very sorry if that is the...
No, I'm saying 9002 already has text that is quite similar to the two normative statements you have there, though not identical.
Yeah.
Okay. So like...
I mean, it talks about pacing, right? And I think it requires the application to tell that you want to pace, which I think is unnecessary.
I mean, it has, basically it says you either need to use the entire congestion window or not be pacing limited, and you should not increase your congestion window.
Yeah. Yeah, okay.
Is that not, I mean, minus the fact that it's a should, not a must, I think that's equivalent.
I mean, it requires the application to tell that it's pacing, right?
No, you cannot use pacing as well with 9002.
Yeah, that's okay. Yeah, but if you pace, I think
then it's just, you need to use the C-wind, otherwise don't increase
it. It would play out in the same way, I think, that I agree with, yes.
Okay.
So we're just trying to find simpler words for the same thing. That's basically it.
No, that's fine. Okay. I guess my point is, I'm not sure it's worth bothering to update it.
Yeah.
Thank you, Ian. All right, that looks like the end of the queue. So this is going to be a deeply interactive session, so I hope you all have your buttons ready to click on poll answers. We're going to do a whole pile of them today. So for our first question, who's read the draft? Wonderful. Click yes, please, on your laptop. I will give it another second, and then we will go on to our next fun question. So this is good. So we've got about 10-ish people who've read it. We'd love always to have a few more. Send comments to the list and or file GitHub issues. Life is good. All right, for our next question. we've got 3 for each of these, except it ate my question. Why can I not click start? Do you want to click start?
I mean, I don't have a question.
I got you.
No, just tell me the question. What's the question?
Oh, apologies for the noise.
Mm-hmm.
All right, our next question is this a problem we actually want to solve? You see my difficulty.
Oh. Yeah.
This is going to be fun if questions don't work.
Mm-hmm.
Yeah. We've each clicked start. Who would like to actually raise their physical hand and say this is a problem that we should take on? Very nice. All right. It's kind of sad not to make a humming noise. If you want to make a humming noise at the same time, go for it.
That isn't working.
All right, no worries. We'll get some connectivity soon. Wonderful. Thank you so much. Yes. That is, what would you say, 30-ish? You want to put them up again and I'll count faster? Wow, estimating is hard. 18. Who thinks we should not work on this? That's why anonymous shows of hands are more fun. All right, and if anybody would like to chime in the chat, that is wonderful as well. We have 1 extra from the chat, so make that 19 for the notes.
The Q tool is also stuck.
That isn't working for me. By the way.
Gotcha. Fun times. Welcome to the queue. What would you like to say, Matt?
Matt Mathis, I think one of the things that wasn't really touched on directly, but there does need to be a very clear boundary between this work and a new experimental CWIN validation work, because as Neil noticed, there's a slippery slope between the two.
Exactly, that's what we're trying to do.
So we're trying to keep this very tight to just this. Yeah, thank you. Ooh, magic. For our third question, we'd like to use this document as a starting point for that solution. The real question is, can anyone respond successfully? Oh, we have one lucky individual. I had to refresh the whole Meetecho interface, if that helps anybody. Yes. We need some pacing, I think. All right, if there's anybody who can't get to the poll and wants to just raise their hand, that's also okay, and we can do some back of the napkin math, but it looks like it's working now. Fantastic. All right. That is a very good signal. Thank you all for your button clicking and your excitement and willingness to work on cool things. All right, thank you, Michael.
Thank you.
Okay, next up. Yes, we'll refresh the slides in a second. Next up, we have Neil to talk to us about BBR v3. All right, and you should have slide control, Neil.
Okay. Yes. Okay. Great. Thanks, everybody. I wanted to just give a quick update on the status of the BBR draft and the nature of the changes. With this new incarnation of the BBR draft, this is a CCWG draft, and there are so far 3 co-editors, myself and Ian and Joseph Bechet from Meta. And then so just a quick overview of what we wanted to talk about today. We just kind of wanted to outline the changes in the draft and provide a roadmap for readers and maybe implementers of BBR v3 who are reading the draft, and just wanted to invite folks to read it and offer comments and gauge interest in making this a working group item. So at a high level, you'll find a link to the new draft, which, as I said, is in CCWG. These are the co-editors. Obviously, this is work based on a lot of work from a lot of people over the years, but these are just the folks who are working on the editing of this particular draft. The high-level changes since the previous version of the draft include the following. One big change is that we've moved the draft to GitHub to make it easier for folks in the IETF community to collaborate and offer pull requests and file issues, things like that. We have incorporated the delivery rate draft, which used to be a separate draft. We've incorporated the text of that draft inside the BBR draft just to make it easier, so we're not having to maintain two separate drafts with dependencies from one to the other. And you can click on that git commit URL just to see exactly how we did that. The other main changes are several bug fixes and parameter tunings that we talked about last July in San Francisco. And then you can find those in the git commit log by just looking for the string BBRV3. And then there's a fair amount of just editorial wordsmithing for clarity and readability and updating references. So I have a couple eye charts here for folks who want to drill down into the details of what changed. This slide summarizes the BBRV3, the main changes that are interesting, which we already discussed last July in San Francisco. And then you can find here the correspondence between these slides that discuss the changes and what those changes look like if you visualize the dynamics of the flows, and then the corresponding git commits that update the various areas of the draft that are describing those changes to the algorithm. And there are two bug fixes there, and then a set of parameter tunings that are basically inspired to reduce loss rates while keeping throughput pretty much the same. And then there is a collection of more minor changes that are less interesting, various small tweaks and bug fixes and changes that were made over the years to the code that we wanted to update the draft to reflect those as well. And that's pretty much it. This is just a reminder. So this is code that's running at Google. All of the internal WAN TCP traffic at Google is using this. And then all of the TCP traffic from google.com and YouTube to users over the public internet is using this. And we do have some experiments on the Quick side that are running code that is pretty close to this, although not exactly the same. And I think the goal is to converge the Quick and TCP code to be using pretty much the same algorithm, but we're just not quite there yet due to developer resources. And yeah, so that's pretty much the update. We're inviting folks to read it and offer comments either in email threads. You can file GitHub issues. You can post GitHub pull requests, whatever feels most convenient. Yeah, we just wanted to gauge interest in moving further with this. Thanks, everybody.
Thank you, Neil. John is in the queue.
Yeah, I had a question. At the ENRW yesterday, there was a presentation that claims BBR3 went backwards in terms of fairness, being closer to BBR1 than BBRV2. And I don't really know any details about which version of BBRV3 they used, but do you know anything about that paper?
I'm not sure if I know anything about that. I'm not sure exactly which paper that was. I have seen some papers go up in various places that that have that kind of result. And I think if you think about the dynamics of the changes, you can understand why that would be. And we've been able to reproduce issues like that in the lab as well. I think, this is an area where we would like to continue to make improvements. We're open to suggestions. And, I think we do hope to continue to make improvements over the years in coexistence. It's a kind of a thorny problem, but, we'll continue to work on it. If you want to if somebody wants to shoot me a pointer to the exact talk, that would be great.
Yeah, I'll send it to you.
We have a Jonna that's almost in the queue.
I am in the queue. I just can't get to the QR code because I think it's behind Neil on the screen. Hi, Neil.
Hey, good to see you.
I wanted to say that backward fairness sounds like a really exciting thing to think about. But I was going to say here that this seems like a perfect candidate for like an experimental. I don't know what the goals are for CCWG in terms of but to the chairs, at least what I'll say is that this seems like exactly the type of thing that you want to be doing here. So to the question of making it a working group item, I know it's not a question that the chairs have asked, but I think they should observably be there. Its relevance and its importance to the community is well understood. I'm glad that that folks are contributing to it. This, however, shouldn't mean that it's a standard that we encourage everybody to deploy. It should just be something where we are able to document the current state and be able to drive it that way.
Thank you. Yeah, I think so. We're going to talk about this a little bit later on in the session, but we absolutely have the ability to choose between experimental, standard, et cetera. And a lot of that we've talked about kind of having our bar be something that is widely deployed, provably safe, all that kind of stuff. And so as we're talking about, can we meet that bar with either the current form of these things or changes to any of the congestion controllers? With each one, I think a lot of what we were doing in 5033 biz was defining that criteria for where do we fall on either side of that split based on the evidence that we can gather from each algorithm.
Matt Mathis. So one of my worries in a bunch of different places is that there's much too much emphasis on what I refer to as bug compatible with Reno. And this is something that this community is the right community to discuss, is to find out whether or not, where to draw the line between, if the scale is bigger than such and so, Reno has no hope of doing well, so don't worry about it. And that Neil has drawn that line particularly conservatively, although it's probably moved since the last time I looked at it. And I would rather move it back, but we can do that. Neil can't do that. And so that's why I want it worked on here.
John Iyengar. I think Neil can do that. Neil, can you push a commit to do that? Sorry, that was a joke. But I think what I will say is that, yeah, I mean, I think we can create a fuck Reno working group. But I think this might be it, actually.
That's the point.
No, but I do think that there's the relevance of real world data from deployment is very useful. And I think we should bring that into this room, but that's the point of an experimental to me, is basically you publish something and then you get data on it and you share that. So yes.
Christian Uitema. Yeah, I mean, I think I'm with Matt on this because the change, one of the changes in BBRv3 is to space out the prop up transition much more than the previous version. And that's nice from the point of view of not being worse than cubic, but it's bad for us because that means that it takes a long time to detect that the bandwidth of the link has increased. And so that's really a trade-off. And yeah, the working group shall opine on this kind of trade-off, because is it okay to make your solution worse because of cubic? And I don't know.
That's exactly the problem I was referring to, that BBR has been made sluggish and somewhat cautious in environments where it wouldn't need to be for technical reasons. It's that way for policy reasons, because it would not be appropriate for Neil or Google to unilaterally say, well, we're going to deploy a congestion control that's going to hurt everybody else. This working group can make the decision, the value judgment at what level of features we're willing to tolerate.
Yep. And I think that's one of the reasons that we're all here together to talk about this stuff. And I think one of the other things that we're talking about as we consider making BBR working group item is, as we hand over change control to the IETF and to the working group, where we go with that debate is something that we all need to be on board with. At the same time, we all are realistic humans who recognize that the thing that we write down and what people choose to ship are the same, because we all have goodwill and we understand the risks associated with diverging from that, not because we have any real authority to force implementers to do something different.
Martin Duke, I mean, obviously 5033 bis is a lot about this. So we have a guiding document for it, but I would like maybe echo, I would like to also encourage Neil to maybe be aggressive, because I think it's easier for the working group to rein him in terms of being aggressive about stuff than like for us to make BBR more aggressive. So I would err on that side to the extent that you have data that you can support it. Thanks.
Yeah, yeah, I guess I'm next in the queue. So yeah, I just wanted to say I agree with everything that everybody's been saying so far. I just wanted to also add that definitely it's not my goal to be bug compatible with Reno, and I agree we don't want to spread out the bandwidth probing too far and give up the potential benefits of probing more quickly. Where I think BBR as an algorithm has a lot of room to improve is that I think by being smarter about potentially using more signals like RTT signals as short-term indicators of congestion, it might be able to do a better job of both keeping queues low and reducing loss, both for the sake of the BBR flow itself and for the sake of the throughput of any Reno or cubic flows that might be coexisting with it. So I think there's a lot of room for improvement, both in the general health of the queues and in the speed of the acceleration and in Reno and cubic coexistence. I think we can improve all of those together and get some nice results. But it's going to take some work.
Cohen is up next, and then I think Jonathan virtually in the queue.
Yep. Can you hear me? Yes. Okay. Yeah, I think there are opportunities to indeed improve, let's say, the Reno behavior, or at least for the classic, the loss scalability or the responsiveness to loss. But like for dual pi square, it is important also to have a kind of a reference to measure what is now the assumed rate in the classic category, and how do we drive L4S to match more or less that rate. So just throwing away everything, and of course it's good to avoid also loss in the classic category, but as long as there are loss-based congestion controls, there should be some way of coordinating and signaling, let's say, what is the assumed rate here. And I guess also delay-based congestion controls at a certain point will experience loss and need to match this. That doesn't want to say that we should be Reno loss compliant. I think there is an opportunity to make at a certain point when the rates are higher and the BDPs are higher. We do that already with cubic. To go a bit farther, because also cubic becomes unscalable. Is there a way that we can make this loss pattern more scalable? That means there will be more loss potentially on high link, or we can sustain also more loss on high BDP paths. But I see there an opportunity to let's say correct that curve from that point. But I wouldn't want to throw away the whole mechanism, because I think it's important mechanism to signal in a loss-based classic category what is around the right rate or the fair rate that we can use.
Thank you, John.
Jana Iyengar again. I don't have any more jokes this time. I'm actually trying to understand what Christian and Matt said means, because if you say that, I think it's perfectly fine for Neil or Google or anyone for that matter to deploy something that is more aggressive. They do it all the time. They're not asking us for permission anyway to begin with. But if we only document behavior that we find acceptable to our brains, that's a problem. I want Neil to document this stuff that's happening in the wild, because it's a way of understanding how to imagine the protocol that's running there. There's a difference between experimental and recommendations, right? If we are saying that by recommendation, we recommend that you can be X times more aggressive than Reno, I don't know where we stop, because then it's not just Reno, it's cubic, and then it's L4S, and then it's whatever else, and then it's different conditions and situations. So I don't know that we can really go down the path of saying, is it okay for Neil to be more aggressive? Well, Neil's not looking to us for permission to be more aggressive at Google. But I'd like him to document the work, how it's actually deployed here. This is why I said that experimental to me seems like the right way to do it, because that says that there's an experiment, there's data that can keep coming to the working group from it. But ultimately, we are documenting something that's happening and the decisions that are being made elsewhere. We can engage with those decisions and try to understand the consequences of those decisions and try to influence them. But I don't think that we can really say how much more aggression is okay or not. Nobody's going to care.
Mo?
Mo Zanetti, on the fairness and aggressiveness topic, just to catch Neil up, I think the NRW paper, it took like about an order of magnitude of Reno or cubic flows to achieve parity with BBRV3's rate. And that wasn't alarming to me, because while the research methodologies typically just flow in an abstract sense, if you look at the operational deployment, a lot of this is geared towards eventually going over quick. And that's a very heavily multiplex transport usually. So it's not unreasonable to think that what we're calling flow is actually, 20 or 30 subflows. And so that begins to muddy the waters about, the traditional, research approaches where you want things very controlled. And so you want the variables to be controlled and not have, these extra degrees of freedom to have all this multiplexing and everything else. But in the real world deployments, I don't see a problem with having an understanding that this heavy flow could be 8 to 12 or 15 times of a Reno or cubic flow. And way back in IETF 84, when we had the congestion control workshop that founded RMCAT, that was the first conclusion that almost everybody arrived at, that TCP friendless would not be a goal for a single flow, but it may be weighted fairness for TCP flows. And that was deemed okay for a single media flow back then. So now today, when we look at a single quick connection flow that may be 20 or 30 substreams, I think it's okay to veer off from strict flow friendliness compared to other congestion controls.
Thank you, Mel. Zahed would like to make a comment.
Jahed, I just wanted to understand a bit like what Jonna, you were talking about. I mean, bringing. So when I was designing congestion control algorithm, I was designing everything, the test case, test bed, and everything on my use case, right? Then I come to IETF and show something, and I get a feedback like, hey, Jahed, you have not looked into this kind of thing, that kind of thing, and all these things. That improved the congestion control algorithm. That improved how I was testing my congestion control and all these things, right? That's the value basically, Neil or whoever comes with the congestion control algorithm to CCW will get the benefit of like looking into these things. So my thinking is like, yeah, we might actually start with experimenting some things, but at some time we need to decide, like, is this good enough for our internet? Is this good enough for go for like a standard or like more than experimental thing? I understand like there are like BBR1, BBR2, BBR3, BBR4, 5 might be coming, but somewhere we have to say like, okay, this is it. This we have done enough, and we're fine with this one, and this working group then produce. Is that something that aligned with what you're saying, Jonah, or you'd like to see like this all the congestion control work happening in CCWG, actually the outcome is experimental? Because for me, congestion control improvement is a never-ending thing. But sometime we need to just decide, like, this is good enough for our internet, and we stamp that one, ship it, hope internet doesn't melt down, but we keep improving after that.
Right, we're never going to stop iterating. Yeah, go for it, John.
Just to respond quickly to that, what you just said to me is an experimental. I don't want to get into the document type conversation, but I think that literally to me is, I mean, yes, it has to still go through. Otherwise, it'll be informational or something, or independent stream, right? If you're just publishing what you're doing, if you're engaging in the working group, you're taking feedback. But ultimately, when you push it out there, it is an experiment, and we hope the internet won't melt down, as you said. But you come back from that and you do revs of the document later. But to me, it is still an experiment. I want to be careful that this is the gap between recommending what people should do on the internet versus the experiment. That should be clear.
I mean, the thing is, like, I think I understand your thinking, but I mean, one of the reasons that we created this working group to actually have a standard congestion control algorithm. If that's never will be achieved, I think then we need to rethink what we're doing here, because you can do this kind of things with ICCRG and stuff like that. So, I mean, as I am saying, at some point, the community has to decide what's good enough and then ship it. And keep doing the research. I mean, I mean, today I saw something like, okay, they were saying like, hey, BBR is bad in a geo satellite network, but that might be they're looking at it a different perspective than Neil have been looking at it. So, I mean, we can learn from each other, definitely, but sometimes we need to say this is good enough. We have improved our experiment with our like congestion control algorithm in an extent, like we have touched upon the corner cases. We are satisfied with what we're doing. We're satisfied with the fairness and everything we're talking about, and we are happy to ship it as a more than experimental, perhaps. That's my thinking. I mean, that's what I'm saying.
Thank you. All right, we need to keep moving timing-wise, so we're going to start a poll. This isn't just have you read this particular draft, but have you read any of the recent BBRs in general? And while you're responding to that, couple of thoughts on the discussion we were just having. One of them is very much the value that we bring as a working group is a place to have some of those ideas, to think of what is this edge case that we should test. But at the same time, one of the things that I think we've all said we explicitly don't want to do is ask authors and people who are bringing congestion controllers to go fetch infinite rocks of infinite cases. And so a conversation that we are likely to have, we talked about this a bit at the hackathon, we'll keep talking about it more in this room, is how can we as a working group contribute to helping make these pieces of data obtainable, right? So how can we help people have a test bed? How can we help people do hackathon style participation where we come and you say, hey, I want to try a different tuning for my congestion controller. Let me test it. And how does it interoperate? How does it compete with different flows? So a big part of this is also what can we as a community do to enable that kind of experimentation and enable that kind of data collection, likely in simulation, to help provide that input. Then I think we talk about, especially CCWG as an IETF working group, we build on top of that by using actual real world data from how is this going, how does it behave in the wild, at scale, on the real internet, and things like that. So to Zahid's point, I do think we are trying to have actual proposed standards in some cases. It doesn't have to be everything that we do here. But we are never going to stop iterating. That doesn't mean that we don't say that you know, we've run this through our suite of criteria, and we think that this is sufficient for us to go with right now. All right, so we've got 34 folks with a yes on having read it, and up next we get to talk about, is this a thing that we should work on? How is our refresh going? Hey, it works. All right, we get 1 poll per refresh. I was going to say, you may also need to refresh every poll. It's a real test to see if you're awake after lunch. So this is really what should the working group take on BBR as a congestion control algorithm that we think is something that we'd like to standardize. We'll discuss exact standards track for experimental versus not. Christian has a clarification question.
Yeah, clarification question. I mean, I am not sure about the rules of the game because BBR up to now has been a Google project. So is it clear that adoption means that it becomes an IETF project?
That is part of the plan, yes. So the working group, the congestion control working group here would take on change control for this BBR. That doesn't mean that we're going to ask Google to stop iterating or stop making improvements, right?
And you confirm that's exactly what Neil is proposing.
But that is the that is the conversation that we're having, yes. So, and I think a big part of this comes to, you know, when we shipped TLS 1.2, we did not decide that that was the end of it and we weren't going to make any further improvements ever, right? So this isn't quite the same problem domain or space, but this is, are we willing to say the IETF is going to recommend, ooh, nice refresh. The IETF is going to recommend that we, if you would like to use BBR, this is a good form of BBR that should be safe to use. And we've just spent a lot of time talking about what that safety criteria is in 5033 BIS, right? Oh, it was so close to putting up the third poll.
Just to check for the notes, did you say that the intention is to give IETF change control to the document?
Yes, correct. All right. And for our third poll and our fourth refresh, the current draft is a good starting point for this work, i.e. do we take the current BBR v3 and evolve it to meet our criteria? One of the things that we are really good at as a community is coming up with random weird edge cases that we'd like people to go test. A big part of that is we need to, I think, help test that and help bring that data. But when we talk about, hey, we can't force people to deploy changes because this is the IETF and we write documents, we are also asking people to have implementations, ideally more than just one, right? So we're looking for multiple implementations. Interoperability is a little bit different in a congestion control space than with many IETF protocols. But we're still very much looking for, can we prove that these are safe and use real world data to motivate changes that we're asking people to make?
Can I add something?
Yes, absolutely.
Thank you. So again, 5033 BIS has a list of test cases and use cases. So this is not strictly a question of bring me a rocks. I think we have protections against that. Now that said, it's meant to be a somewhat timeless document, and so it doesn't like specify, you know, link specifications and all that. So there is some wiggle room there, but this is not just like whatever we kind of improvise as a test case. There's actual like a battery of things we're going to look at.
Absolutely, yeah. And I think operationally, we'd really be interested in chatting with the group about how do we turn that into something that is approachable for people, especially researchers and folks in academia who'd like to propose changes to one of the algorithms that we're talking about. Would anybody who said no to this document as a good starting point for the solution like to come to the queue and tell us why? We had two folks who were uninterested in this particular starting point. All right, we've got Michael in the queue.
Yeah, I think it's very long and has a lot of pseudocode, and I'm uneasy about that. I mean, you know, there was not yes, no, maybe. I mean, I'm unsure if this is the ideal starting point. It's, I mean, I have a feeling that if we would start with a shorter one from scratch, we might end up with a perhaps simpler and cleaner document that doesn't have so many heuristics nailed down and built in as a hard-coded suggestion. But
thank you. So some of the concern that the pseudocode contains choices that the actual text does not? In that the pseudocode picks particular things that are not otherwise specified in the text, as you must use this value or something like that?
Yeah, it might be too concrete. There's a table of all these parameters in there, and there are, I don't know. I'm unsure. You asked me to come, so I'm unsure about it. I don't want to say it's a bad starting point necessarily. I'm not convinced it's a good one.
Thank you. Yep. All right. Moving on forwards in the interest of time, but this is definitely a discussion that we'd like to continue, both around starting point, and I think you'll see the meta discussion of how do we decide that something's good enough to cut a version and actually go with it is a beautiful thing. Next up, we have Christian to talk to us about some changes we could make in BBR.
So I guess I have to stand on the course.
We have some flexible cameras. You can stand anywhere you're comfortable.
Okay. Good afternoon. I'm Christian Wiedemer, and it's a bit of a continuation of the previous discussion. Pardon me? Okay. Good afternoon. I'm Christian Wiedemer, and now I'm speaking into the mic. Okay, so this work is work we have done with my colleagues Suhas and Colin on using BBR to control real-time communication. And basically what we are testing is sending media over quick, and the media is structured in a way that is very similar to what people may know as hierarchical encoding. It's actually a simulcast in which for a given media stream, we are sending several versions, say 360p, 720p, 1080p, 4K. And then we are using the congestion control in real time to make sure that in case of congestion, the low bit rate gets priority over the high bit rate. So that is done inside the quick packet scheduler to know which stream are sent first. So in case of congestion, if I don't have enough bandwidth to send everything, I will send the priority packets that belongs to the stream for 360p or 720p, and not necessarily wait a bit before sending the stream for the higher definition. The goal being that in case of congestion, the user sees continuity of the video without extra latency at the price of a lower definition. So basically the point here is that to do that, we have to sense continuously the state of the network. And we sense the state of the network by looking at the state of the congestion control, which in our case is implementing using BBR. To answer the previous question, I did actually an implementation of BBR based on the draft that Neil published. Okay, so we do that. So in theory, you see it's perfect. In theory, if the network gets congested, we stop sending the high definition video, we send the low definition one. And when the capacity comes back, we send the high definition again, and we are always, the best quality without overloading the network. In practice, there are a few problems. There are a few problems, at least here, which are problems with BBR. The first is during the startup phase. BBR obviously was designed to facilitate web traffic and traffic which is being streamed and things like that. The startup phase stops when we have, for 3 epochs, no increase in the measured bandwidth. And at that point, what BBR does is, because you are almost at the right value, you have actually almost estimated the capacity of the link. So it's sending data at 2.77 times the bandwidth with a C-wind, which is set to twice the BDP, twice the product of the mean RTT by the estimated bandwidth. What that means that basically your era will be CWIN limited. It will last for 2 BDPs, so it will last for 2 RTTs. And during that time, the queue will raise to 2 BDPs effectively. So you are basically getting twice the delay for 3 eras, which means 6 RTTs. If you are doing real-time communication, twice the delay for a long time is not good. So we'd like to see BBR do that. That's probably the kind of stuff we'll do in the working group, discuss that. We have a big dependency, however, on BBR is because of the fixes for cubic. The initial estimate matters a lot. If the initial estimate is too low, because it will wait a long time before coming up, it will remain low for some time, which is not good. What did I do?
You did nothing wrong. We'll come back. Keep going.
Okay. We have then other issues which are linked to the fact that we are working a lot with Wi-Fi networks. A lot of the video is sent to computers that are sitting on Wi-Fi networks. And Wi-Fi networks have issues of their own, like the suspension or the fact that they can go bad very quickly, which I will show in the next slide. And then we have 2 issues linked to the bandwidth limited nature of the video. Because even if we send 4K, in most cases, when the video codec is just sending differential encoding, the bandwidth is not that high. So the bandwidth will be lower than what the link actually permits, and the application will tend to be bandwidth limited. That will change every 5 seconds or so when all the videos are getting refreshed, because at that time there is a peak of traffic. But so we have this alternance between rare peak of traffic and relatively low bandwidth. And there are a lot of issues there, like we observe a downward drift of the bandwidth over time because of interaction between BBR and the application. And we also observe that in some cases, the state will remain in the probe bandwidth state because when the application is bandwidth limited, BBR effectively never exits the probe bandwidth state. So next. So first, let's go back to Wi-Fi. The one thing we really hate about Wi-Fi is that every second or two, your Wi-Fi driver decides to stop the radio. And they stop the radio for, we don't know exactly why, but we believe it's because they are switching the radio to other frequencies to scan those other frequencies. And the net effect is that you will see the transmission just stop. I mean, there is no radio left. Packets are being queued. You are not going to lose any packets. Those packets are being queued. They are being queued before the driver on your station or at the router in the Wi-Fi network, because when the driver does that, it first sends a Wi-Fi control message to the router saying, hey, keep all the packets for me for some time, please. So the packets are being kept. And when the driver decides to come back, when the radio is turned on again, all those packets will flow very rapidly and situation will be back to normal. That doesn't play well with BBR because what you have is you'll get an RTO because 100 milliseconds is larger than the RTO. You may get several RTOs, in fact. So your bandwidth will say, hey, that link is almost broken. Bandwidth will fall to very little. Even when that comes back, it will take some time to come up again. So that's not the effect. The other effect is because it takes an RTO, a PTO to detect the situation. During that PTO, the station continues to send packet. And those packets that it continues to send are typically the wrong packet. You will continue to send the high definition packet when in fact, given the low bandwidth, you would like to send the other ones, the high definition. basically you would like to send only the high priority packets, but you get a priority inversion.
So you have a minute and a half.
Okay. With a question? Yeah.
If you want to take
Okay,
a question there.
Okay. Next problem is that even if it were not for the suspension, Wi-Fi can go back very easily. Basically, it suffices that you move your device a little bit and the antennas come out of alignment, or somebody moves in front of the antennas. And you can easily, we have cases that are very easy to reproduce in which the transmission drops to a very low bandwidth. The loss rate increases a lot. So basically, you have the link has changed. And BBRV kind of deal with that, but it deals with that slowly. It deals with that after the first PTO. It decides to reduce the window, etc. I mean, there are mechanisms, but net is that you have all the same problem as in suspension at the beginning, like priority inversion. It takes a long time to realize that you should only send the low bandwidth packet. And after the bandwidth is restored, you have a very slow ramp up, which means that it doesn't go very well. So all these are kind of stuff we observe in practice and that we would like to see fixed. I'm running out of time. So if you read the draft, there's a lot of proposed fixes, basically make the startup more like HiStart++, exit the prof bandwidth when the dealing increase, etc. And I'd like to make another slide for one other suggestion we have. Damn. Oh, okay. It's basically of detecting the loss of feedback. A lot of the issues we have is that if the link disappears or gets back or get bad, it takes us a long time to find out. Basically, you have to wait for a full PTO to find out. And what we do there is that we observe that in normal condition, you are going to receive a steady stream of acknowledgements. And if a suspension happens, or if your transmission goes really bad, the stream of acknowledgement will disappear. And we want to basically notice that the stream of acknowledgement disappears because we can notice that much faster than noticing that we don't much faster than a PTO. I mean, that's as the diagram shows, okay? And so we have added that signal as a control signal for BBR, that if we have that signal, if we have this loss of feedback, we basically freeze the window, get into what BBR calls the conservancy mode, so that we don't pile up more packets in that thing, because piling more packets when you should not be sending them is bad for real time. So that's what we do, and we go back to normal. So basically, we can match the issue list with the various solutions that we have. And our goal is to basically make our BBR colleagues, our goal was to make our BBR colleagues at Google aware of that. And please consider updating the BBR draft. Now, if the BBR draft in fact becomes an IETF draft, I mean, that becomes make our IETF colleagues aware of that and get some proposed change on the BBR draft. So that's what we are doing now, socialize the issue. Suhas has prepared a video that shows the experience, the change with those changes. We can have discussion on all the details. I'm sure that Suhas has plenty of idea and will tell me I'm wrong. Oh, no.
So we are at time, so please, we're going to drain the queue, but try to keep the comments quick.
I'm Stuart Cheshire from Apple. I don't remember ever telling you you're wrong, but I don't know, maybe. Anyway, I came to the microphone because I just particularly wanted to 100% agree with you about Wi-Fi suspension. It's funny how the timing works out. Just in the last few weeks, I've been working on this in the context of L4S and just basic TCP retransmission timing, that when TCP is trying to measure the round trip time or quick or anything, and compute the retransmission timeout. If you're sending a bunch of packets to the Wi-Fi layer and then it just sits on them because it's busy doing something else, it's doing a channel scan or something, then that can result in spurious retransmissions. And our conclusion was, you really should be measuring the round trip time from the time the packet leaves the device, not from the time you hand it to the firmware and then sometime later it actually leaves the device.
That's a partial solution, Stuart. That's a partial solution because it's the other side as well.
Absolutely, yes. Yes, I just came to say, I think for all of us in this community, better cross-layer communication between the Wi-Fi driver and the IP layer and the transport protocol about what's going on would be really valuable. If the Wi-Fi layer is going to sit on the packets for good reason, it should tell the transport layer, you know what, I haven't sent those yet, and you can keep giving me more, but I'm just going to queue them up. And that would be really valuable information, especially when latency matters and doing anything real time. The stuff we didn't care about 10 years ago is really critical now. So same conclusion, different background.
Yep. All right, Subir.
Yeah, thanks. I'm Subir Das. I have a question on the Wi-Fi side. Is it what kind of which version of Wi-Fi did you use in the experiment? Is it Wi-Fi 5 or Wi-Fi 6?
We have measured that. Suhas, can you?
I think we did measure on Wi-Fi 5 and Wi-Fi 6 and different platforms.
So the next quick question is that when you are sending this video, are you also listening the audio?
Yes.
Okay, so then I understand that there's why the suspension reason is there, because audio is coming through Bluetooth, right?
No, audio is blocked as well at the same time.
It's blocked. Okay, that's fine. But I agree with Stuart that if there is a data available on this, the behavior on the Wi-Fi, I think it would be very helpful. Then I can actually take it to the IEEE.
Yeah, I mean, that's true.
Okay, let's move on to Suhas.
So just a very quick comment about that, because I know not everybody is an expert on Wi-Fi. There's lots of reasons your Wi-Fi radio, like if you're walking around the house, it might want to scan the other channels to see if there's a better access point to roam to. There's a lot of complicated stuff going on.
Yeah.
And there are good reasons for that. We just have to deal with it.
So Haas from Cisco and mock enthusiast. So one of the things with the mock working group is to make mock work for real-time calls as well as the streaming. And we started playing with BBR and we realized the BBR is really good algorithm, but it does not work very well for the real-time use cases. And that's a gap that we want to fill. So for adopting mock to support real-time use cases, some of the fixes that we've been working on for a year and a half of experiments, it has shown a clear difference in making it work for the real-time requirements. We would like some form of the solution to be discussed in this working group and considered for the next version of the BBR. Thanks.
Thank you. Magnus?
Yes, I was thinking about this brace a bit and the issues with the application limit and the codecs. I mean, that's why Scream has some rules that saying, okay, you can actually send faster than the congestion window within limits, but just so that you can get your variation due to, for example, video codecs out in a reasonable time and try to maintain the pacing, etc. So I wonder how pragmatic we want to be in the future here on these things, and saying how for certain type of media or data streams, how strict are you to following the congestion controller when you actually have data to send and you sometimes application limited.
That's not a question.
No, it's a comment.
Okay.
Thank you, Magnus. Thank you. All right, we're going to do a quick poll here of I have read the draft. I think it sounds like our goal here is to kind of fold this into some of the BBR work that we're doing rather than have this be a separate document. Yes. So, and I think this is a really interesting mechanism. So definitely worthy of additional discussion. We've had some good comments so far. But cool, okay, it looks like we've got a couple folks who've read it, some folks who might go read it soon. And then we'll kind of fold this in as we talk about some of the other BBR topics.
Thank you.
Thank you, Christian. All right, next up, we've got Rue to talk about some HPCC++.
Roy, are you there?
All right, we can see that you're in the session, Ray, but you're not sending any audio or video. Give it a second to get going, and then we can always come back.
Okay, let's come back and do a search for. Oh, there's Roy.
Yeah, sorry, I just rejoined.
Beautiful.
Okay.
The floor is yours.
Yeah, so we just want to give updates on our progress. So this is a joint work from many folks, and so HPCC is a mechanism that leverages the precise information you can get from network devices to understand the congestion status along the path, along the devices, so that you can make a timely and precise decision at the sender side. So next, please.
You should have slide control if you hit the right
Oh,
arrow key.
really? That's great.
Fancy.
Yeah. So this figure shows the working scenario we're targeting. So we are focusing on those data center hyperspeed networking for those applications like AI, ML training, and storage database applications. So there, the requirement for bandwidth and latency is very, very high, especially for today's network. And in the backend, the bandwidth is huge for the applications, and any latency loss will cause a significant loss in the network capacity. So that's why we want the ultra low latency. In the meanwhile, we want to have a high throughput. So these are the scenarios we are targeting. I just want to give a quick overview of our mechanism, how it works. So HPCC is a precise congestion control mechanism to leverage the features in today's network devices where the networking ASIC today can provide those in-band telemetry capacities. So those in-band telemetry capacity can provide, can insert metadata into the packet to tell, hey, when the packet goes through this switch, what's the current queue length of this device, and also what's the link utilization of this device when the packet goes through. So actually the packet can carry on those information and hop by hop and to the destination, and destination can send the information back to the sender. So the sender actually know when my packet going along the path for every single devices, I get a precise information, so the sender can make a very timely and precise decision and how to either increase the sending rate or decrease the sending rate accordingly. So previously we present our evaluation results, and today I want to give a summary on our deployment side to support the CCWG. So this is the congestion signaling that has been deployed in one of the largest cloud provider, and also we're working together with so it's been proposed from another working group, IPPM. So that draft is focusing on how to define the telemetry format. So the different vendor can implement the same the format. And for this draft, we're focusing on the algorithm part to make sure that we are along the same congestion control algorithm. So to support the CCWG, they have a fixed size aggregated metadata. You can see that in the packet header fields, and currently they support the compact mode and the expanded mode. But right now in our draft, we focus on the compact mode. And so in HPCC, we have two parameters that calculate the link utilization, is U1 plus U2. So the U1 actually calculate the congestion detected by the Q length. So actually is the Q length divided by link bandwidth. So that will determine what's the extent of congestion this link experience. And U2 actually capture the link utilization. So the idea of CSIG is that they only leverage one of them, not both at the same time. So HPCC will leverage both, but the CSIG only leverage one of them at a time, because the observation they observed is that when you have a Q like U1 larger than 0, so the U2 should be always 100%. I mean, likely 100%. I mean, there's some transient behavior. So that's why we, in that case, if we already observe there's a queuing buildup in the link, we don't necessarily need the U2, because U2 most likely will be 100%. On the other hand, if you don't have a queue buildup, which means that U1 is equal to 0, there's no queue buildup in the link, then we don't have to collect U1 information. We only need to U2. So in this case, U2 will be less than 100, because if it's above 100, it will certainly build up the queue. So this is the key idea, can save the space when you log the data into the packet header fields. Second part, we also handle a couple of edge cases where when the traffic switch the path, either due to routing changes or due to load balancing, so we only need the two consecutive packets collected in the sender side to identify there's a new path, so we can get rid of the old condition status and start to build the conditions status for the new path. And we can use the so here's a slightly different mechanism when we quantify the queue length. In HPCC, when the packet is about to eject from the egress queue, and we log the queue length, saying how many packets are behind this packet are already in the queue. That's our queue length definition, which will give a very immediate response when the congestion just build up behind this packet. The difference here for the CSIG that they only leverage the signal packet to say how much delay this particular packet experienced in the queue. So that's
Quick
a
time check. You have 3 minutes.
Thank you. So that's a slightly different. I mean, that include the QA time?
Yes, technically yes.
Okay, I can quickly ramp up here. So that's a technically studied slightly different, because if you look at how many packages just behind me when I about to send from my egress queue, they will give you the early notification, versus if you allow a packet go through all the way from the tail of the queue to the front of the queue and then calculate the sojourn time of this particular packet, it has some delay, and then our algorithm will not recommend to do that, but that's an estimation or approximation that CSIG is doing. That's a slightly different. So in algorithm perspective, we can support CSIG with the format defined by PPM, and also we put the CSIG format in our informational draft as well. So we have two drafts. One draft focusing, the main draft focus on the algorithm, and also second, the information draft focus on different implementation in terms of how you're gonna inject the telemetry in the packet. Yeah, that's all for my presentation, and appreciate your time, and any feedback will be welcome.
Awesome. Let's have Neil.
Hi, yeah, and nice talk. I saw a couple places where it seemed to be talking about taking the queue length and dividing it by the link bandwidth. One thing I wanted to mention is, as far as I know, most cloud deployments typically are going to have multiple queues in front of every link to support quality of service or differentiated service, whatever you want to call it. And so I think in cases like that, we don't really get what we want if we just kind of take the queue length divided by the link bandwidth, because there are potentially many other queues that might have queued packets, and those would be contributing to the latency of the packets as well. Anyway, thanks.
Yeah, that's a great observation, and actually that's the case for the cloud environment as well. So we have two takeaway from here. I mean, for those traffic controlled by HPCC, we have some other traffic controlled by TCP, right? So we assume that traffic controlled by HTTP is under high priority because people care more about the latency there, and then they typically will assign higher bandwidth share, which is minimal bandwidth guarantee of the link. So in most cases, we got enough bandwidth. The secondly, we talk about the multi-queue support in our draft. And we have a pseudo algorithm also ready. And basically, the key idea is when we see the congestion, we can always fall back to the minimal bandwidth guarantee. That's the mechanism people are using, is a weighted round robin. We can always fall back, say this particular queue, although it's shared by other queues, other traffic, but the device is guaranteed for this particular queue. That's your minimal bandwidth. We can always save to fall back to that rate, and going further, it's a trial. We can do additive increase to try if we can grab more bandwidth. If there's a node, other traffic in other queues, we can do that. Thank you.
Wonderful. Thank you. All right, we're going to do our quick little interactive portion here. So first off, who's read the draft? And one of the things that we're thinking about is kind of, as we talk about getting deeper into some of the discussion for these, how much do we have bandwidth to take on? And so one of the questions that we're about to ask is this kind of data center and really high bandwidth congestion control something that the working group should work on? And that can be, do we want to work on it right now? That could also be, that's something that we think the working group should work on, but later. So yes is a valid answer for both of those to the next poll. We will have a separate conversation at some point about the now and the ordering. That'll be when we talk about charter. So right now it's just we would like to see CCWG talk about this at some point. It does not have to be tomorrow. All right, we're going to close this down and do the next one. We're going to refresh and then do the next one. So we're interested in working on this kind of topic at some point in the life of CCWG. And if anybody who has responded with no, as opposed to no opinion, would like to come to the queue and talk a little bit about why, that is always welcome, but not required. Stuart is in the queue. All right, closing this pull down and opening the next one while Stuart talks. Go for it, Stuart.
I said no opinion, but I think I should say why. My first reaction to this was we work on the internet here, and all of these things where like the buckets have to be configured, there's clearly no way that on the global internet, right, you can't have them all configured differently. And then at the same time, I'm thinking, we developed this technology here, IP and QUIC and TCP and things, that have use beyond just buying stuff and doing online shopping. And I do that myself. We use IPv6 for home automation with Thread. So on balance, I'm thinking IP is a good technology to use in the data center. And we should be making that possible. So as long as this is clear that this is for a very specific use of IP technology, I think that is very much in the charter of the IETF to make our technology applicable and useful in different scenarios beyond just web browsing and email that we all do day to day.
Thank you, Stuart. Yep. All right, and our last question about document being a good starting point, and Gori wanted to make a comment as well. Same question goes for this, then we're going to move rapidly through the other things because we've got a few more agenda items to talk about and only so many minutes. Go for it, Gori.
So Gori first. Yeah, I agree with what Stuart said, but I also want to know who is the customer. So, I mean, when we do an internet protocol, we're expecting multiple parties to come and want to use that technology. Some people are providing a service, some people are developing implementations, and we need a standard to work between them. So I think it's important when we look at data center cases that we have multiple customers for this. That means multiple different vendors using it, but also different people developing things. Then maybe it's worth us investing in a standard. Otherwise, this is going to take our time up, and who needs the work?
Thank you, Gori. I saw a couple of thumbs up in the room as well. It is worth noting that our charter explicitly mentions data centers and real-time protocols, but does not require us to do anything in that space. So I think perhaps some of the feedback that I'm hearing here for you, Rui, is also, let's make it clear to folks what is the expected use case for this, who are the kind of intended audience, and if we can get a number of different proponents who all say like, yes, we'd like to use this, then that is a really good signal for everyone else as well in terms of where we allocate our time.
Hello, can you hear me?
Yep.
Yeah, so that's a great question. And for the customer, you can see that this is one of the biggest, is Google, right? Is already deployed and supported, and also some other company also supported, like Alibaba, my previous employer, is already deployed, and people on board because people care more about, really care about the latency for those emerging applications like storage or AI training. And for the reason why we want to have this draft is because many different vendors, you can check the author list, the different people from different companies, they want to have alignment, how to support this customer, what's the data format, what's the algorithm you want to use. So we have been put into discussion, many discussion on this. This is why we want to have a draft ready so people can on the same page to align the algorithm and data format so they can work with the customer, work for the customer more easily. So that's our initial motivation to do this.
Gotcha. Thank you very much for the clarification. In the interest of time, we're going to keep going through our next talk, which is Search, a new slow start algorithm. Mark's we should have some slides going. Beautiful. All right. We've got a slightly abbreviated timer here to make sure we can make it through. So let's keep an eye on time and take us away.
Thank you, everybody. Mark Claypool, professor in WPI. It's near Boston. It's a small engineering school. Jay and Feng are engineers at Viasat. Miriam's a PhD student that's worked on this. So we jump right in. So again, if you're looking at slow start, ramp it up the C-wind, you'd like to hit the capacity point before you exit slow start, so near where you want to be. If you do it too early, especially for links with high RTTs, you're going to have underutilization. So we say that's kind of a too early exit point. Conversely, if you sort of overshoot, you end up going past it, causing a lot of loss, exit too late. Ideally, we'd kind of hit this sweet spot, near capacity, exiting slow start. We call this a choke point, makes for a nice acronym. So choke point. So we start looking at, so how does current TCP with high start enabled, or the default in Linux, how does that work? And how does that work over wireless networks? And spoiler alert, it doesn't work too well. And let me show you a few things. So if you take a look, we started looking at, of course, Viasat's geosatellite links. You're looking at the congestion window ramping up exponentially, doubling each time, roughly each time every RTT. You want to hit that capacity in a narrowband geosatellite link. You're going to hit that, right sweet spot. You're going to hit it right there, and you'd like to exit there if you can. Turns out with the GeoLink, it's about 12 seconds in. It can, again, high RTTs, about 12 seconds in, you're going to hit that. You turn on high start, you run on TCP, you hit it way early, about 1.3 seconds. So it exits slow start really early, causes underutilization, takes a while to get up to the speed. If you turn off high start, of course, you're going to hit the other side, you go way past it. And again, some of that's because there's these large queues that build up. So there's this huge area that you keep on going without knowing what's happening, and with a lot of packet loss. So it doesn't work well. And this is not unique, though, to geolinks. This happens for LEO links. So Starlink did some measurements in Starlink. Same idea. Numbers are different. You hit the congestion point about 400 milliseconds in. High start always exits early, about 100 milliseconds in. High start just causes it to say, hey, I'm done. Exit slow start. It's on the left. On the right, if you don't do it, you overshoot. 0.6 by 600 milliseconds in. Happens every time. 4G LTE, we did some Verizon be the provider. We did it for this. And again, some of the same, you always are exiting before that congestion point with high start on. It's always at about 100 milliseconds or so, averaging about 3.3 is sort of where you're going to hit the sweet spot for our test bed here, where we're running this. Big queues, so you go over it, about 2 seconds worth at the end. So all these are working pretty poorly. It works for more typical networks, so LAN transfers across Wi-Fi. We've done this on our campus network at WPI. Sort of the same. It's not always under, but it averages high start on, again, before the congestion point, just exits early, caused by those timing issues in these wireless networks. So what we're looking for is something better. So that's search. So let me tell you a bit about search, kind of how it works, and then a little bit on performance. So the acronym slow start exit at right choke point, so search. And then again, it starts with the premise that if during slow start you're sending roughly doubling your bytes every RTT, and so you expect that to kind of continue. And you can sort of see in this picture on the left, it surpassed the capacity. So when that happens, you actually don't deliver the bytes. So the delivery rate, what actually comes back to the server, you get this sort of flattening, right? Can't deliver more than the link capacity. So you can compare those two. And you can keep track of the sent bytes, but you can also just do this with the delivered bytes. And you can actually take the delivered bytes and say, hey, I'm just going to keep track of those. And then you can go ahead and compare them. And so that's what the algorithm is going to do. It's going to try and look at the delivered bytes and the sent bytes. So, so taking a look, a bit of the code, this is a few things to talk through here. So if you try and predict those sent bytes, so in roughly, let's say it's T4, you say, hey, I know what I sent last time at T3. It's like 2A, so it should be 4A. So I can actually compute that, and I can compare those two things. I can say, how does my current delivered bytes compare to the ones that I sent? So I can compare at T4, I can say, hey, ours are the same. If they're the same, cool, looks pretty good, life's good, keep going. But then if, you see at time T5, if I do the same computation, oh, I'm sorry, I have to normalize it too, because I need to normalize it because of the different link capacities we have to handle. So if I take a look at that normalized difference and it's greater than some threshold, so like at T5, there's a difference there. Then you say, hey, I've passed my capacity limit. And so you'd want to exit slow start at that point. So that's a quick intro, high-level idea motivation. There's some challenges, of course, to making it work beyond my PowerPoint slides, right? So how do you build this? The first one we had to face is sort of the ones that were facing us in the geosatellite links, which is variable RTTs. Here's a picture of the round trip times in the geosatellite link over time. So this is just a download over a link, so 12 seconds of time. And the RTTs on the x-axis, those are hundreds of milliseconds, again, base of 600, but they go way up. All of this is before congestion. There's no congestion on the downward link here. This is not a congested link. These are just variable RTTs, and they're not caused by congestion on the forward link. They're caused by ACK scheduling on the backward link. So lots of RTT variability, and that just messes up high start, but it also makes timing using round trip times hard. So holds for high start plus, for example. And so our solution is to smooth over this variation with a window. So you use a window of data. So don't just look at a single RTT, but look at multiple RTTs to try and smooth over that variation. So that's sort of the first challenge. And then if you're trying to keep track of delivery rates, you have, of course, limited memory. We know that you can't track every ACK and store it as a history because you keep this per TCP connection. So we have to limit memory use. So the way we do that is we allocate sort of we aggregate over multiple time blocks. You take that window, we break it into blocks. Think about it like an array, call those bins. So we have a series of bins. And so now you're actually aggregating, keeping track of these. You've made it more granular. And then we actually also only process, you only do search processing at the bin boundaries. So you don't have to process every ACK, but only at these bin boundaries. So it saves processing also. So those are two challenges that make it practical to deploy that we've overcome with the windowed and then the bins. This is the pseudocode. It's in the RFC. I don't expect you to read that. I'm not going to actually talk through it. I think it's fairly readable, but take a look yourself. At a high level, I'll just do a few bubbles. You initialize stuff at a TCP connection, and then every time you receive an ACK, you do some updating of the bins. You update what's been happening, so the data's been arriving. At the bin boundary, so when you actually get to the end of it, you say, okay, let's see if we should actually slow start. So you compute the delivery rate, the predicted previous delivery rate. You compare those to the threshold, normalize them compared to a threshold. If they're above the threshold, then you exit slow start. Right, so that's pseudocode. Take a look at that if you want to talk about it at a break or something, happy to. Let me tell you about a few key things in any kind of code. There's some parameters that matter. And we spent a fair amount of time working on these. We have some theoretical, some measurement stuff, justifying the parameters. And there's a few that make a difference. That window size matters. So how much do you need? How long do you need to make that to smooth over that variation? So we did some Fourier analysis on the signals, and you pick the peak, and then you use that to drive how large the window could be. Some details are in the paper we presented at WowMom just last month. And again, large enough to make it so you respond, to smooth out, but not too large so you can be responsive. Window factor of 3.5, so that's 3.5 times the initial RTT. That's our window size that we, based on all the measurements we've done of all those networks I mentioned. The second parameter that matters is the how many bins, so that bin size. So how many bins do you need to use? So again, you want enough bins that you have aggregated and reduced load, but small enough that you have granularity to represent the network. So again, another thing, we've done some sensitivity analysis. How much do the number of bins matter over lots of different conditions, and our current recommendation is 10. And you need extra bins because you have to roll back that window, 15 extra bins, so 25 total. And again, those possibly could be adjusted, but those are I think, decent recommended starting points. And then the third one is what's that threshold factor? And so we did some theoretical analysis of C-wind growth and did that based on noise. And currently, it has to be something positive, but 0.35 works well for most of the network conditions we've been testing. All right, so those are parameter selections. And again, look at details in the paper. The RFC doesn't have too many of them. It waves its hands, but you can look at the paper for details. Okay, thank you. So I'm going to do one performance evaluation piece, and then I'll wrap up since I know we're short on time. I have a couple in this slide deck, but just the GeoLink and the Wi-Fi link. And let me just show you a little bit how it's working. So if you take a look at, again, this is the C-wind growth with high start on. It looks like it's growing well, but that's actually the cubic growth right there. It's actually exit slow start, and then it doesn't cause any loss. It's underutilization. You turn off high start, and that window shoots way up. Great. Better utilization, and yet causes lots of packet loss. This graph is packet loss here. Search works pretty well, has the same ramp up, exits, then is in congestion avoidance kind of probes, causes very little loss also. So we get sort of the benefits of the throughput. Under the hood, this is sort of what search is doing. That blue line is the predicted sending rate. The green line is actual delivered rate. And so they diverge. And so kind of when they diverge, that's when you're like, hey, something's going on. And if you normalize that difference and compute the threshold, that's this graph. And I'm sorry, normalize the difference and compute that normalized difference graph. That's the blue line. When it crosses the threshold, that's when it exits, is indicated there. So yeah, that's I know that's quick. I won't show you the Wi-Fi results. I'm just proving this. Works well over Wi-Fi 2, sort of a different set of analysis. Let's go on. We've built Linux kernel modules for it and tested it. Sorry, I didn't mean to go through that slide. We built kernel modules and tested it. It's worked well. We have a couple different ones out there. We've actually also built it in open source quick library, that's the quickly H2O library, and have some results there. Works well also for that. We've done a bunch of different tests on the networks I mentioned. We're trying to upstream it, get it in the kernel, but happy to have people grab these as is and use them if they want to try them out. And that is mostly my wrap up. Again, high start is clearly broken over these networks. It just does exits way early. It doesn't do what it's supposed to. Search has some reasonable properties. I think that makes it work pretty well. Improves utilization, reduces packet loss versus turning off high start. And we have if it's helpful, if you search -ss.wpi.edu, will take you to the project page. That's where we have, again, the code modules, plus there's all the papers that we published on it and documentation. And that is all. Thank you.
Wonderful. Thank you so much. Gori is first in the queue. Then we have Ian and Neil. Let's keep it snappy so we can make our way forwards. But very
Gori,
interesting work.
yeah, thanks for this talk. And of course, when we were doing the careful resume thing, we also looked at high start because it happens to play well after careful resume. But yeah, all these problems. Was this 9046 you were using as the basis? Was it HiStart++, or was it HiStart? Because I think that's a major difference.
Yeah, this was HiStart. So it's in the Linux, default Linux kernel's HiStart. We have done some preliminary work with HiStart++, and HiStart++ also exits early over geosatellite, very early. It has, HiStart, as you probably know, has an extra stage, so it takes longer before it really decides to enter congestion avoidance, and it has a slower growth rate, so it has some slightly different properties, but still underutilization for some of the links we've looked at.
Would love to follow up on the HiStart++.
Yeah, thank you.
Ian's web. Yeah, I was actually just going to ask if you were comparing to HiStart or HiStart++
Yeah.
in the original slides. That was all.
Yeah.
But this looks interesting. Thank you very much.
And Neil.
Yeah, Neil Carbler here. So one thing I think it would be worth incorporating into the document is consideration for exiting spuriously based on receive window limits or application limited behavior. That's something that we found is critical to incorporate in BBR's code, heuristic for exiting slow start, because those are very common issues to run into, and you don't want to exit spuriously because of those. Another thing is that my reading of the draft, it has 25 bins of data, and presumably that's about 4 bytes, maybe a U32 for each. So that's about 100 bytes worth of state, which would kind of double the congestion control state on a Linux TCP connection. And so there might be some concerns about incorporating that into mainline Linux. So we might want to, it would be great if there's a way to iterate on this algorithm and reduce the state concern, the state use, and maybe take this on as a working group item when there's a version that is incorporated into a major transport stack, maybe.
Yeah, cool. Thanks, Neil. Those are great comments. I mean, just real quick, the application rate limited, I think we handle that. That's a case we do handle. I think we're okay. We just don't, search doesn't kick in. That's the first one. The memory one's a good one, and we're working on that. I think we can go down in bytes for each storage, plus it perhaps is fewer than 25. And yeah, that's a important consideration. We're considering that also.
Beautiful. Thank you so much. So similar questions as all of our other interactive segments. So I have read the draft, always a good question. Or the paper, that's totally fair, or seen the other presentation. But yeah, I think mostly we're looking for signals of engagement and willingness to review and contribute. This is also really nice because it kind of contributes to our toolbox of things that we use as we develop congestion controllers. So as we talk about in our chartering discussion, both the do we want to take on particular congestion controls, as well as can we spend working group time on helping do this? I think that's really great work. So thank you for bringing this here. All right, for our next attempt at a question. Beautiful. Is this something that we'd like to spend working group time on? Is this something that we want to contribute to, come up with ideas, help test, brainstorm ways to poke it, prod it, and otherwise make it great? I will give that another second as you convince your client to let you click buttons. All right, thank you. And then, is this something that seems like a good starting point for taking on work around slow start and how do we actually achieve a good estimate of a initial rate to, there we go, beautiful. I think it's also one that we will talk about more as we kind of move towards adoption of various things. So this isn't necessarily, will we adopt this tomorrow, but more of a, is this, it sounds like this is a thing that folks are interested in coming up with solutions for, and it seems like a valuable problem to solve, which is really encouraging. So beautiful. All right, let's hop into our next presentation, but thank you so much, Mark.
I'm sorry, can I agenda bash?
Absolutely.
We have 15 minutes. I think it's really important we have a rechartering discussion rather than another paper.
We can do that.
Draft.
one of the reasons that we deliberately put that at the end rather than the beginning is because we believe that our current charter covers all of the work that we've talked about here and our potential to adopt it. And so the rechartering discussion is mostly a editorial. Are people happy with clarifications that we finished 5033 bis?
Okay.
Plot twist. But that said, I think let's try to keep this to a super speedy 5 minutes so that we make sure we keep a solid 10 to go through those editorial changes, make sure everybody's happy with it. But thank you, Martin.
All right, let's bring up Kuhn. We cannot hear you or see you yet.
Okay.
there we go.
Yeah.
All right, we're going to go for an express mode 5 minutes here. So let's go zippy zippy.
It's a short presentation. So just want to give a quick update on the Prague congestion control and maybe in general a bit about L4S. Should have control somewhere. How can I move to the next page? Yeah, okay. So first, quick L4S standard status. So you all know DOCSIS has adopted it since a while. 3GPP also has adopted it in release 18. It has L4S in the RAN, CUDU interactions, low latency DRPs support L4S. And in the next ongoing release 19, also targets for future user plane nodes support in L4S. Then also interesting is that there is in WBA a lot of activity around implementation guidelines for dual price aware and the Wi-Fi MAC. So there were a few comments before living with or coping with what the Wi-Fi is doing. So one of the good things is that L4S can work with the Wi-Fi nodes. If there is an outage, it doesn't mark packets. So only the window blocks then your throughput, and when the packs come back, you continue with the write rate without a reduction. So all of these things can be done if, let's say, you have an explicit signal in the device itself. So that's, for instance, one of the works to have optimal connectivity between an AQM and the Wi-Fi MAC. Then on the other hand, of course, you say we have to cope with all those Wi-Fi outages. Well, actually, it's not necessarily, because a lot of these scanning can be done with site radios, so more improved Wi-Fi chips will avoid these outages. And also one important thing is the EDCA and the MAC layer, the distributed MAC. More and more people start to realize that WMM is kind of a triple play legacy, and it's not future proof anymore, and want to move on and correct these things. So that's also interesting. Like L4S removes the queuing latency, but not necessarily MAC latency. And so in that respect, it's good that we can work on improving the MAC latency for future and maybe existing Wi-Fi devices. Also in BBF, L4S is an L4S project is launched. You can see there will be working on PON and access networks, fixed access networks. So that will also start. Next slide.
Time check. You have 2 minutes. You can advance yourself.
Yeah. So maybe also to give a bit of an overview, what are the Prague objectives? So from the Prague congestion control itself, it's to have an end-to-end low latency service, and to make that deployment of these services easier and scalable. So you have to provide low latency end-to-end, and all your network devices need to support low latency. But L4S, you should think, makes it easier to deploy it and more scalable, because you don't have to guarantee bandwidth. You can adapt the application, and typically interactive applications, they are very adaptive, and they want to be adapted before they see any latency or blockages or drop. So also it's important to know that we first want low latency. So all the design objectives want to control the real speed and not the throughput, which is just a quantity. How much can I send for an adaptive application? The quantity can be adapted, but the speed, how fast the interaction is important. Okay, then, and also L4S offers an interactive service to applications next to the classic and buffer traffic. So it's good to have two in parallel. I'm not going to go into details, but maybe in interest of time, the next slide. I can click myself. A quick update on the Prague status itself. So it's deployed in Apple Quick Prague. Apple Quick falls back to Cubic, by the way. It was released in the latest macOS and iOS. Linux TCP Prague. We have improved a few extra features. There's going to be a presentation in ICCRG on Friday, if you want to know a bit more details on that. We also have a lot of kernel versions available now, and we are working on the upstreaming in release 6.11. We hope to get it in there now. Then also new is that we work on an UDP Prague implementation. So there is a link to a repository. It's still under construction. It's to be able to do the Prague congestion control for UDP-based applications and of course, targeting interactive applications, which immediately can update the source, the generation of the data, and not necessarily have a stack blocking their throughput. So it's a single source C++ file that you can kind of incorporate in your applications. We are working on some examples further. It's being currently introduced in iPerf2, so it will be platform independent, running on all platforms that are supported by iPerf2, and you can do then UDP-based Prague, which has the advantage that you have more precise application level measurements without socket buffers and flow controls and all these things in TCP stacks and even in quick stacks. But of course, quick stacks can be made also more application data source interacting. Okay, we will also add further real-time Prague and also the Cubicon loss. It's the idea to have that in UDP Prague, but also in TCP Prague in Linux. So there are also UDP Prague or Prague-related applications like NVIDIA GeForce Now. They are deployed, and okay, the draft in ICCRG exists, which we need to update to the latest status of the newest enhancements, let's say, in TCP and also in the future UDP Prague. Okay, that's it for me.
Excellent. Thank you.
Thanks.
All right, we've got our poll running. We'll go quickly through our other questions and pop into our charter discussion. For this, I think with regards to Prague, it'd definitely be good to update, to have it match kind of the current reality and ship a note to the list. I think we've seen some pretty good discussion in the past, and there's definitely some real world deployments from which we could gather data. So let's get things updated and then we'll rediscuss from there. All right. Martin.
So to clarify, they're seeking adoption in CCWG and not ICCRG?
So we're having a conversation amongst the chairs of both groups to figure out where we think we should take this work, yes.
Okay.
So this is not a, we think that CCWG is necessarily going to adopt it versus ICCRG, but the question is more, is this something that the folks in this room are interested in working on?
Yes, it was a request from the chairs here to give a presentation on Prague. It was not necessarily an adoption call, so for us it's not, for at least the authors here, it's not.
We're fulfilling our promise in our charter to coordinate with chairs. It helps that one of our chairs sees the same chair in the mirror. All right, let's bring up our, yeah. All right, and I know, Matt, we had an as time permits, which will not permit, but we can bring it back next time or on Friday in ICCRG.
All right, folks, now we've already have heard all these wonderful proposals. Let's bring it back to the high level. If I can drive my own slides, let me refresh that. But as Eric already reminded everybody, CCWG is already chartered to adopt proposals in this space, so we can already adopt proposals in our current charter. And still, we wanted to reflect the fact that we're done with 5033 bis and add some introductory text about what congestion control is, why it matters, and then also refine or focus on, like, now we're doing it, now we're specifying congestion control proposals, and potentially reflect some of the themes that we've talked about a lot already since we started the working group a year ago. So this is just a proposal for some introductory text to start our charter, and we're not trying to wordsmith. Right now, we welcome discussion on GitHub and the mailing list. Can we get a thumbs up, thumbs down maybe for adding this high-level motivation, because congestion control, sometimes people will misunderstand who are not in this room what it is.
I'm sure we will happily wordsmith exactly how we want to define congestion control on GitHub. So this is just, without any words, just seems reasonable to people to have an intro at the top that's just like congestion control's a thing. Sweet, cool. All right, thank you.
You got some thumbs up. And then here's 2 focus topics that reflect themes we've discussed a lot in CCWG so far. So we can always add more of those. And then we already heard all these great proposals, but we might have limited bandwidth to take on everything at the same time. So if people have thoughts on what to do first, prioritization, how much can we take on, and review, and also make sure we help out folks with evaluation, right? How can we make evaluation a collaborative effort instead of only the authors? All right, Matt, did you want to? Oh.
I actually had a comment on the first paragraph, which I don't have a wordsmith for. The on-site tool is being particularly lame this meeting. There's also a missing thought here, and that is the congestion control properties of applications. And what I mean is there's a lot of application designers who say, oh, transport worries about congestion collapse, I don't have to. And if you write an application which every time it retries, it starts a new connection, it defeats the safety measures in the transport. And so, in fact, there are application design issues which are congestion control properties that have to be subject to congestion control properties. And this is all looking inwards into the protocols, but you actually have to look up the stack as well.
Right. Thank you, Matt. Any other thoughts?
Before we dive into the comment, I think the thing that we're most, if we move the slides back forward, the thing that we're most interested in, so there's a pull request that's currently open on GitHub, has a bunch of text. Please come help us wordsmith it. It's easy to find. It is the only pull request on the working group materials repo. So we'll send out a link, but please come help us wordsmith it. It's mostly just updating to reflect that we've finished with 5033 bis and adding that paragraph. So, propose all the text that you possibly can, please. I think the thing that we're most interested in right now is how much do we think we can take on at once, and what should those things be? All right, with that.
Yes, thank you. Greg Mirsky Erickson. I think that, improving the latency is bounded by laws of physics. But what congestion control can achieve is minimizing the latency variation, delay variation. And I think that that's something that can be mentioned explicitly. Thank you.
Thank you. Gory? Thank you for typing and running. We appreciate you.
Gory, trying to think about how we do potential work. I mean, one of the things in 5033 is somebody needs to get data out there about how well this works. This isn't a great venue for discussing that, but somehow that data has to be there and we have to see it. And if we take on that broader scope, that's a lot of heads that have to look at all these different things. So I wonder whether we have to actually just adopt them slowly and actually evaluate them. Then I don't know what happens. I'm going to be very short now. I don't know what happens when we adopt something and then we need to evaluate it and then we need to progress it. So there's kind of like, I don't understand how the mechanisms might work. Do you have an idea how it might work?
We have a pile of ideas that we'd be interested in feedback on. A big one of them is how can the working group help contribute some of that data? Because I think one of the things that's made this kind of work really hard in the IETF in the past is, as somebody who is a proponent of an idea, you end up with infinite work to satisfy a questionably actionable set of questions that are asked. So as Martin reminded us earlier, like we have a much nicer scoping of the set of questions that we're asking, but I suspect we have some appetite for drilling a little farther. So one of the big questions is, do folks have interest in helping, both in the hackathon and some of those kinds of things, helping build this evaluation environment? Can we make it so that when we adopt one thing, we can, I think our most concrete proposal right now is let's pick one thing and adopt it. And as we run through that process, build the tools that we can then apply to the next one. So the chair's proposal is a width of 1 for the first one, rather than a width of 6.
Yeah, Gorik again. Yeah, I like that. We might find there's small stuff that comes up which is actually more obvious and doesn't require that sort of process, but that sounds good. Do you adopt it and then do that, or do you just kind of note it and get that work done before you adopt it? And don't overcommit at the mic in response to that. Think first.
Yeah, definitely. So the idea is that we have to have a scientific study of the pros and cons when we ship the proposal to IESG. So the working group's job is to make sure that evidence exists. It can come from various places, authors, academia, ICCRG presentations, academic papers, all this sort of thing. And we had a hackathon table this time to get started on testing congestion control more broadly. And we will come back in Dublin with that. So happy to have more participation on that topic.
Yeah, I think that's where we come back to. Adoption is where we essentially take over change control of that proposal, and we take on responsibility for helping gather that data, right? So there's the initial bar of, hey, have the authors as the initial thing have enough to show that it's a real serious proposal and a plan with use cases and people who are interested in working on it. But as we go forwards, I think a big part of the reason that we're in this room is because we all want these things to succeed, and we'd like to be able to make progress in this area rather than just see things continue to stall. And I think when we want to see that progress, part of it is now our responsibility to help make that progress happen. So, all right, I see Miria's in the queue. Matt is also up. Pick your order. But
yeah, I'm a little bit concerned. So I think the biggest benefit of having an RFC for congestion control is that you have like a stable reference. I mean, that's why we published Cubic, because otherwise you have like dozen different papers and everybody implements things slightly differently or whatever. The reason why we never published something earlier was because we are afraid to say this is what we recommend and then we break the internet, right? So I think we should very clear that this is not what we do. What we want is a stable reference. That's a benefit. And by putting the testing burden too high, I think it can be easy to drive people away who just want to have this stable reference. So I think that is much bigger value. We just have to like put the right disclaimer on the RC saying, this is not like the best recommended congestion control. This is what you should test on the internet, and this is how it works.
And I think we've tried to write down the litmus test for what are the things that we would recommend, and what are the bars for thing we would recommend versus, by the way, this exists, please be consistent. Yeah.
So at the end, I think the evaluation burden shouldn't be that high, and therefore I think we can actually adopt multiple things as long as those people who work on it come back and actually do the work, right? So why would we limit it to one if there is enough interest in doing something?
Got it. Thank you. All right, Matt, and then we'll
I was going to suggest that we have two different statuses, one of which is adoption, which means we want to have change control, and another one which is monitoring or supervision or something, which means we want periodic reports from the authors, but aren't willing to take it on as something that we're responsible for.
Interesting. For what it's worth, that something along those lines has so far been our litmus test for the delta between ICCRG and CCWG. Of ICCRG as kind of that incubation place where we ask questions and ask for the reports on how the results went, and CCWG is the place where we say, okay, we'd like to take this on and make it a real thing.
So 5033 BIS has guidelines for standards, experimental, and to some extent informational, and there's like no, in terms of just having a stable reference, you could do informational, and there's no testing bar for that.
Yep. So we have built the litmus test. Now is our opportunity to run a real world example against that litmus test and learn from our mistakes. Right. Beautiful. With that, thank you all so much for being here. Have a great rest of the week, and don't forget to come to ICCRG on Friday so we can incubate some stuff.